Hello everyone! Welcome back to my YouTube channel. Again, this is Sir Robinson, your partner in learning mathematics. In this video, we are going to learn about the derivatives of a function. What is really the derivative of a function? And how it is important in dealing calculus. But before that one, let's take a look at these objectives in this video. Because in this video, we are going to learn these three objectives. In short, these three objectives only tells us that we are going to define the derivative of a function using the slope of a tangent line. Yes, I know that there are unfamiliar terms in these objectives, but do not worry, we are going to learn this all together. The main point or the main question of this video is that what is the derivative of a function? How the derivative of a function works? Where is the derivative of a function in the physical world? What is application of the derivative of a function? That is the main point of this video. Do not worry, we are going to answer all of these questions together. But before we answer the question together, or before we answer what is the derivative, let's take a look at these terminologies that could help us understand derivative well. These are the terminologies found in our objectives of this lesson. First is second line. What is a second line? Second line is a line that touches the curve at 2 points. What does it mean? I have here an illustration. Say for example, I have the curve, a parabola. My curve here is a parabola that opens upward. How the second line works? If I have a line that touches 2 points at point this one and this one, and obviously my line touches 2 points, automatically that line is a second line, or that green line is a second line. That's how it works. How about the tangent line? Tangent line is a line that touches the curve at 1 point. Say for example, I have another function here, a parabola that opens downward. How the tangent line works? So, make it sure that your line touches only 1 point of the curve. So say for example, this one. Take a look at that one. There you go. So you can observe your line only touches at exactly 1 point. Therefore, the red line on the green curve touches only 1 point, meaning that is a tangent line. And this line and this point where your tangent line touches on the curve is what we call the point of tangency. Next is the slope. The slope, we believe that is the behavior of our line, how it works. And slope only applies to our line. So we believe we already know this term and we are familiar with this term. That is the slope of a line. In short, it determines how our line works. So these are the terminologies that we have to identify. Let's try to define derivatives now. As you can observe, I have here an illustration where I have a point P and point Q. As you can observe, I have 4 point Q here, but they are not different point Q. They are the same. It only shows that my point Q here moves closer and closer and closer to my P. So now, let's try how the derivatives works. This is my first line. My first line is that a point P and a point Q. It touches 2 points, therefore this is a second line. And obviously, in order to find the slope of this one, we have to take a look at this. On the x-axis, I have an x And also, it approaches to the triangle x. What is the triangle x means? Triangle x means the change of x. Say for example, my x here is at 0, meaning no change at all. If my x moves, in short, it will approach to the triangle x or the change of x. Say for example, the distance is 3. In short, from 0, there is a change 3 units. That is how the change of x works. Of course, every time we deal a graph, we are dealing two variables, x and y. Same with the x-axis. We have to identify also the change of our y-axis. This y, same thing. No movement at all. No change at all. Y. And it moves upward. That is now the triangle y or the change of y. Same thing. If my y here is 0, no change at all. If it moves upward, meaning, say for example, this is 2. From 0 to 2, there's a 2 units change in the distance from y and then the change of y. In short, this x, change of x, y, and change of y are the slope of the function. It determines how our function works. Again, let's go back to our graph. Our graph tells us from point P to point Q, and that is a second line, right? And this point Q are the same point Q. It is just that our point Q moves closer and closer to our point P. Note that as the point Q moves closer and closer to the point P and approaches the P, the second line becomes a line that will pass only through to the point on the curve. Look at this illustration. My second line moves closer and closer and closer. Again, my second line moves closer and closer and closer. Therefore, if my second line moves closer and closer to P, my second line will become a tangent line. Very good. The second line becomes the tangent line to the curve at the point P. This is how the slope of a tangent line works. In short, the derivative of a function works by simply in this form. The MSL, what is MSL? M here is the slope of a second line approaches to the slope of the tangent line. In layman's term, the derivative of a function works by simply converting the second line into the tangent line. From touching the curve at 2 points to touching the curve at 1 point. That's how the derivative of a function works. Through this illustration, we come up with following remarks. Take a look at these remarks on how these things works. First remark is that, again, we convert that slope of the second line into the slope of a tangent line. We call the line with the slope MPL. MPL again here is slope of the tangent line as a tangent line of the graph of the function. Say for example, I have a function f of x at the point p of x of f of x. What is this p of x? What is this p of x f of x? This is the point of tangency. Let's go back to my graph here. This one. This is my P, the point P here. That is my point of tangency. And that's what I'm trying to say about P of x and f of x. These are your point of tangency. Second one is that, as you can observe, we try to use the change of x and the y of x or the slope of the function. Through that one, we come up with this one. But the question is, How do we derive that one? In this video, do not mind how we derive that one. I'll present that one to my next video. For now, just think that this one refers to the difference quotient, or in the physical application, that is the average rate of change. That's how the derivative works. The difference quotient, this is the difference quotient f of x plus change of x minus f of x all over the change of x. That is your difference quotient. And that is interpreted as the average rate of change. How often that your function changes. Next one is that the derivative of a function f of x with respect to our independent variable x is function f with an apostrophe. This one, as you can observe, you can see an apostrophe over here. Wait, where's my cursor? Okay, I've seen it. As you can observe, you have an apostrophe here, f apostrophe x defined by, how are you going to read this one? Read this one as f prime of x. In short, every time you encounter f prime of x, you are now dealing with derivatives of a function. And that f prime of x, f prime of x, is equal to, take note, what do you call this part? That is your difference quotient, correct? Or the average rate of change. As you can observe, going back to the graph earlier, our point Q gets closer and closer to our point P, meaning it approaches where no changes at all. Let's go back to my graph. In this graph, let me erase this some of this part. Okay. In this graph, as you can observe, in this graph, you have point P and point Q. So meaning we have changes here. As your Q moves closer and closer and closer to P, meaning no changes at all, it approaches to 0, meaning from the beginning, from P to Q, there is a change. If it goes back to the origin, there is no change at all. That is why in this remarks, we use the limitation as the definition of the derivatives. How it works again? As you can observe, this one in red box, that is what we call the difference quotient, where your change of x approaches to 0, because the changes approaches to no changes at all. In short, the change of x here is what you call the point Q, and the P here is the 0, meaning your point Q approaches to P. In short, the change of x, in order to identify the derivative of a function, meaning the changes happen in a function, should approach to where it started, or no changes at all. Therefore, we have to use the definition of the limitation, meaning the limitation of this one, this is your difference quotient, right? In the second remark, as your change of x approaches to 0. Meaning, how are we going to get the derivative of function? By using this limitation here. Again, let me clean that one. Very good. This is the definition of the derivative using the limit definition. The limitation of the difference quotient as change of x approaches to 0. Every time we deal the derivative, we have to use this limitation, where f of x is the function considering changes given over there. Still confused? Don't worry, we are going to illustrate it more to have a full understanding. For the next remark is that this one. Again, how do you read this one? This is the f prime of x. Prime spelled as P-R-I-M-E. Prime. F prime of x exists, meaning if the derivative exists, then the function is differentiable at a given x. And the process of finding the derivative is what you call differentiation. Next is another remark is the notations used in the derivative of a function with respect to x. Why we are keep on saying with respect to x? Because our x here is our independent variable. Other than that, we used to have a function with respect to x. These are the notations used in finding the derivative of a function. Again, the first that I presented earlier, this one, f prime of x. This one, f prime of x. So that is f prime of x. You can also use y with the apostrophe here, y prime. We believe f of x is equal to y. For another notation is what? dy over dx, where y here is your, this one, where y here is your dependent variable, and your x here is your independent variable, dy over dx. You can also write this one, big letter D, the notation number 4. The d of x of f of x, meaning the derivative of the f of x. You could also write d of x, y. So these are the notations used in finding the derivative of a function. Take note, you can use any of this one. But to begin the understanding of the derivative, I usually use f, the notation 1 and notation 2. Okay, so to avoid confusion. Okay, so this is one of the application of the derivative. That is what you call the instantaneous rate of change, or the velocity. I believe velocity, acceleration is already presented to you way back then. To expand the horizon of understanding velocity, let me present you the derivatives. And that is one of the applications of the derivatives, finding the velocity, acceleration, and a lot more. Same thing. As you can, look at this one. Wait, I'm still finding my cursor. Where's my cursor? Okay, I find it here. So, as you can observe, that is ds over dt, meaning second and distance and time. If you still remember, the velocity, distance, and time, right? That is how we interpret velocity. So, same thing here. So, the f of t with respect to time, or ds over dt, where s is the distance and t is time, and h approaches to 0. Same thing, as you can observe, it is same with our previous remark. That is the average rate of change, wherein we change h as that is equal to h there is equal to the triangle x, or read as the change of x. Okay, so these are the notations. So in summary, these are the some of the remarks we get in finding the derivatives or defining the derivatives of a function. Still confused? Do not worry, we are going to broaden the horizon. In short, in layman's term, derivative is a rate of change. Meaning, when you talk about derivative, we are dealing how frequent, how often the function changes in a period of time. What are the examples in the world that change? Yes, indeed. Everything in the world changes. Because in this world, the constant thing is change. From the bacteria, from the growth of hair, from the profit, the increase of money in the bank, and a lot more. everything requires change. In short, for us to describe the changes of any function in the world, we have to deal derivative. Because the science of derivative is the science of change. I have a lot of examples. Example 1, example 2, example 3, example 2, finding the tangent line. And of course, I think this is somewhat connected to you because you can able to really appreciate it one because this application, finding the average and instantaneous velocity. And for example 4, and a lot more. For this, for example, I will solve this one in my next video. But this time, I do hope that we understand how the derivative works. In short, derivative is a rate of change. Still confused? Do not worry. I still have lots of videos for you to cover everything that is important in the world of derivative.